Welcome to this lesson, and in this lesson we are going to talk about orbital elements. We use artificial satellites a lot in these days for navigation purposes, for weather forecasting, for telecommunication, for defense, etc. And it is important for us to know the exact position of a satellite at a particular time. And we need to calculate the position of a satellite, position and velocity of a satellite in a given future time as well. So we make use of certain parameters known as orbital elements or classical orbital elements. In short form, we say it COEs. So we make use of these orbital elements to specify the shape, the size, the position of satellite, etc. So let us look at the orbital elements. The first orbital element is the semi-major axis. It is denoted by the letter A. The semi-major axis describes the size of the orbit. Now, if you remember back, we have the first law of Kepler, the Kepler's first law of planetary motion, which we borrow for the satellite motion as well. So, from the Kepler's first law, it says that every planet revolves around the sun in an elliptical orbit. Similarly, every artificial satellite revolves around the Earth in an elliptical orbit. It can be a circle, or it can be a very elliptical path. So, the semi-major axis gives the size of the orbit. Now, we know that the point closest to the Earth, when a satellite revolves around the Earth, the point closest to the Earth is called the perigee, and the point farthest from the Earth is called the apogee. So, the semi-major axis is half the distance between perigee and apogee. So, here we can see that this is perigee and that's the apogee. And the distance from perigee to apogee is called the major axis, and half the distance is called the semi-major axis. So, in case the orbit is circular, the semi-major axis will be the radius. So, here we have different orbits with different semi-major axes. So, this one have a semi-major axis from here to here, and the outermost one will have the semi-major axis from here to here. So, we can see that the semi-major axis describes the size of the orbit. The second orbital element is called the eccentricity. It is denoted by the letter E. And this orbital element describes the shape of the orbit. By shape, I mean that if the orbit is circular or it is highly elliptical. So, if we have a look at here, we have different orbits with different eccentricities here. We have the circular orbit with eccentricity 0, and as we go up, if we have an eccentricity, let's say 0.95, the orbit will be highly eccentric. The eccentricity can go above 1 as well, but then the satellite will not be orbiting Earth. So, again, the semi-major axis gives the size of the orbit, and the eccentricity will give the shape of the orbit. The third orbital element is called the inclination. It is denoted by the letter I. The inclination describes the tilt of the orbit. Now, here is how we calculate it. We have a plane called the equatorial plane, which is the plane we assume in the plane of the equator. And we have an orbital plane marked red in this diagram. So, it is the angle between the equatorial plane and the orbital plane. If the angle is below 90 degrees, that is 0 to 90, it is called prograde or direct, which means that the satellite will be moving along with the movement of the Earth, that is the rotation of the Earth. If the angle is above 90 to 180, that is something like this, if it is 135 degrees, it is called retrograde. That is, the satellite will be moving in the motion of the satellite will be opposite to that of the motion of the Earth. And if the inclination is 90, it is called a polar orbit. Now, the next orbital element is called right ascension of ascending node, or RAM in short. So, it is also called the longitude of ascending node. And this orbital parameter or the orbital element describes the twist of the orbit, and it is indicated with the letter omega. So we have the satellite orbit here, and let us say the satellite is moving in this direction. So we have the equatorial plane here, and the ascending node is essentially the point at which, the longitude at which the satellite crosses or intersects the equatorial plane. And since the satellite as well as the Earth is moving through space, we need a fixed point of reference to say this. So what we use here is, this line is the point of reference, and this line is a line from the center of Earth through the Sun on the day of the vernal equinox. So that's the reference direction, and the right ascension of the ascending node is measured from that direction to the point where the satellite or the orbit of the satellite intersects the equatorial plane. The next orbital element is called argument of perigee, and this describes the orbital rotation or the location of perigee in the orbit. As we have explained earlier, perigee is the closest point in the orbit to the Earth, and as we can see here is the perigee, and it is measured in angles, and the angle is measured from the point of the ascending node. So if the perigee is here, the angle would be like this red line. The next orbital element is called true anomaly, and true anomaly is the orbital element that describes the location of the satellite. All the orbital elements that we have discussed earlier gives us parameters regarding the orbit, the size of the orbit, the shape of the orbit, the tilt of the orbit, the twist of the orbit, etc. But the true anomaly gives us the position of the satellite. So if a satellite is here, the true anomaly is described in angles, and the angle is measured from the perigee. So for example, if the satellite is here, the true anomaly will be this angle. Now, even if we have all these orbital elements, in order for us to calculate the position of satellite in a future time, we need to specify at which time these orbital elements are accurate. And this time frame where all these orbital elements are accurate is called the epoch. So if we have the orbital elements for a satellite in one epoch, we can extrapolate it. We can calculate the position of the satellite, the velocity of the satellite in a future time. And it is very important because, for example, if we have a defense satellite or if we have a remote sensing satellite, and if a scientist is studying about a particular location, it is important for him to know when the satellite will be over that particular position. So epoch is important. So when we specify these orbital elements of a satellite, we also specify the epoch at which those orbital elements are accurate. So this is about the orbital elements. Thank you.